Hello, and let's talk about different types of waves. There are a few main types of waves, including transverse and longitudinal. Now, when a wave moves, let's say it's moving left to right, how the particles are vibrating determines whether it's transverse or longitudinal. In transverse, they would be perpendicular, so the particles might be going up and down when the wave moves left to right, perpendicular to that direction. A longitudinal wave is one where the particles move parallel to wave motion. So if you're going for the wave left to right, then the particle is also vibrating left to right with the same axis, the same parallel to it. So let's just consider a longitudinal wave. If you can, try to focus on a point inside the wave. Notice the point itself simply goes back and forth, left and right. The overall wave, however, appears to be moving to the right in this case. So each particle motion is going back and forth, left and right, parallel to the wave motion, which is heading from left to right. The particles themselves cause the wave to move, but they don't go along with the wave. The particles stay in place. Recall that a wave transfers energy, but not the actual particles, not the actual matter. So in longitudinal, it's parallel to motion. The particles vibrate back and forth. They don't go along with the whole wave, but the energy of the wave, the kinetic energy in this case, of the wave is transferred along the system. Compare that to a transverse wave. And again, if you focus on a single dot, you'll see that the transverse wave here tends to be moving to the right, but the dots are only moving up and down. So although the wave looks like it's moving to the right, the particles are moving perpendicular to that, up and down. It may be difficult to see from this picture, so let's make it a little more simplistic here. Again, focus on a single dot. Notice the single dot appears to be moving kind of to the right, but it's just moving up and down. If you can see them, the red dots might be easier to look at. The red dots are slowly moving up and down, while the wave moves to the right. So as a crest approaches the dot moves up, and as a trough approaches it, the dot moves down. However, overall, the wave moves to the right. Longitudinal is parallel. Transverse is perpendicular. So if we were taking a slinky, in both cases the wave would move to the right, but to make a transverse wave, we would go perpendicular or shake it up and down. Versus longitudinal, we shake it in and out, left and right. If we were to go ahead and separate up these different things, one of the most important longitudinal waves we're going to discuss is sound. Transverse waves would be waves like you might see in a sports stadium when people get up, do the wave. Water waves, and very importantly, light. Earthquakes are actually made of both longitudinal and transverse waves. In an earthquake, there are several waves that happen. We're not only going to talk about the waves that travel through the earth. We're not going to worry about surface waves. But when you're talking about an earthquake, there are two main waves that come from it. They're called primary or P waves and secondary S waves. Those are waves that appear at the location. So primary waves would get there first. Secondary waves happen second. So in an earthquake, a tremendous amount of potential energy is stored up in rocks, and then in an instant it's released through the motion of those rocks, causing it to compress the rocks around it. The primary waves would travel through as a compression wave, as longitudinal waves. Following behind it, moving up and down would be the secondary waves or a transverse wave. Now, if we're talking specifically about sound waves, one of the things we're really talking about here is, again, a compression wave. So longitudinal waves compress the particles together, and they cause a series of compressions and rarefactions. Rarefactions is kind of the opposite of compressing something. It's stretching it out. It's producing an area of lower pressure. So as the plunger on the left-hand side here pushes in, you can see that it creates an area of higher pressure, a compression, squeezing the particles together. As it pulls back out again, it takes the particles and lets them spread outwards, and that's called a rarefaction. That's an area of lower pressure. So longitudinal wave is also sometimes referred to as a compression wave, where it has areas of higher and lower pressure. Waves are typically discussed as sine waves. So how does a longitudinal wave compare to a sine wave, which is more in line for a transverse wave? Well, the areas that are compressions are equated to higher pressure. So those are the crests in the wave. And lower pressure, or the rarefaction areas, equate to the troughs. So a longitudinal wave is an area of higher pressure, lower pressure, it's compression, rarefactions, but it can be described as a sine wave if we change the sine wave to areas of pressure: higher pressure, crest, lower pressure, trough. Two other types of waves are mechanical and electromagnetic. Mechanical waves are the waves that have to travel across matter. These are most waves. A vibration of matter, say the vibration of water particles or people in a stadium, air particles, are mechanical waves. Because mechanical waves require matter, mechanical waves cannot travel through a vacuum. On the other hand, electromagnetic waves can travel across matter or vacuum. An electromagnetic wave is caused by variations in electric and magnetic fields, which are discussed in a later unit. In terms of what type of waves they are, most waves, again, that you would be familiar with are mechanical waves. Water waves, stadium waves, earthquake, sound. They might be transverse, they may be longitudinal, but all of them travel across matter, so all of them are mechanical. On the other hand, electromagnetic waves are light. That includes visible light or things like infrared, X-rays, gamma rays. Electromagnetic radiation will be covered in a different video. Key takeaway, though, here is that sound waves are longitudinal and mechanical. They are parallel motion and they must travel across matter. They are vibrations of matter. Light waves, on the other hand, are transverse and electromagnetic. The particle motion is perpendicular and it's capable of traveling through matter or vacuum.